Vanakkam. Welcome to this course on biomedical instrumentation. We are interested in looking at EEG. As a start, we looked at central nervous system in the previous video. As I already mentioned, it is an extremely brief overview of the neuroscience. Because this is a course on biomedical instrumentation, I have limited the neuroscience content to this. But that is perhaps true of respiratory system, cardiovascular physiology, respiratory physiology everywhere. But the neuroscience being close to my heart, I have my other courses on classics in neuroscience and neuroscience of human movements, in which I discuss this in great detail. Each of these is a full 30-hour, 12-week course. Now, in this video, we will look at, or we will introduce ourselves to EEG or electroencephalograph. What is encephalo? Encephalo means brain. Let's see. Encephalo means brain. And brain waves, types of waves in EEG. Essentially, EEG records brain's activity via scalp electrodes. You keep electrodes on the scalp and you record activity that is happening in the brain. Now, let us study that situation, because just on the brain activity may be happening way below the surface due to volume conductor effects. In a previous video, we have discussed volume conduction. That is, if some excitable tissue, say this is the brain, say for example that is the brain, the cerebellum, right, and if some activity is happening here in this place and I am keeping the electrode here. Due to volume conduction effect, I am measuring some activity here. By the way, I might also be able to measure something here, right, because the rest of the tissue in the brain are also conductive tissue. Because of that, due to volume conduction effect, I will be able to measure activity that is happening somewhere deep. By the way, there might be some activity that might be happening here also along the way. So, what you are measuring is essentially a field effect due to multiple neurons. So, for you to be able to detect activity at the scalp, you need to have about activity that is happening in about 6 centimeter squared area of the brain. That essentially represents, in neuronal terms, depending on the average size of neurons, actually that is not the perfect way to study this, approximately 10 to 100 million neurons. That is a lot of neurons. So, EEG does not measure action potentials of individual neurons, but rather they measure multiple postsynaptic potentials that are getting transmitted through volume conduction effects that are seen on the scalp. Okay. So, it is essentially a complex waveform. Unlike ECG that has a typical PQRST template, EEG looks more like noise. So, it is a complex waveform that vary with the electrode position, where you are keeping the electrode matters. So, depending on the broad regions of the brain. So, electrodes essentially measure not just the activity right below it, but rather activity within a certain radius, about 5-6 centimeter radius around that electrode. So, if you keep electrodes too close, then you are measuring activity, you are picking up activity that has already been picked up by the neighboring electrode. Again, we discussed these advantages and disadvantages of having too many electrodes and too less electrodes in the electrode arrays and other such discussions. So, EEG essentially represents the summed electrical activity that you see in the cerebral cortex and deeper structures also, because deeper structures, if there is, for example, there is some activity going on in the basal ganglia, that will be reflected in EEG, except that you do not know what is the basal ganglia signature of that. That is the problem, because if an activity is happening deep below the cortex in basal ganglia, through volume conduction I will be able to see that effect in the scalp electrode also, except that it will be very difficult for me to localize which is coming from basal ganglia alone. So, this is the typical EEG machine or the EEG electrode system, and this is a patient on whom the electrodes have been placed, right. And what you are measuring, the EEG waveforms itself themselves look like this, they are all looking practically like noise, all of this look like noise, right. How do you classify? So, also from this you need to make sense of what the brain is trying to do. Remember, there is the brain layer, deep activity may be happening deep inside, then there is the cortex, above the cortex there are layers of protective tissue, dura mater, pia mater, and then there is the strong bony cranium, bony structure called cranium or skull. Above that is the scalp, above that sometimes hair is also there. Then you place the scalp electrode and measure with the electrode gel. The distance between the surface of the cortex and the scalp electrode can be in the order of centimeters, that much distance. So, what you are and all this dura mater, pia mater, there are 6 layers, subarachnoid space, that entire space there are 6 layers, all these layers essentially attenuate signals. So, what you are measuring at the scalp is a well attenuated signal of what is happening inside, and this attenuation is mostly happening due to these bony structures like cranium or skull and all the other things, right. Other insulating material, for example, right. So, this measures the ensemble activity of many neurons. It is not an activity measurement of a single neuron, many neurons. How many neurons? Sometimes thousands of neurons, sometimes millions of neurons. So, brain's electrical activity, not the entire brain's electrical activity, some anywhere ranging from hundreds to millions of neurons activity using electrodes that are placed on the scalp. These signals are very small means typically in the order of microvolts, peak to peak, actually 10 microns, 10 microvolts from the scalp and up to 1 millivolt from the exposed brain. If you are doing some open skull surgery, then if you are measuring from the surface of the cortex, then you might be able to get up to 1 millivolt, and that is a lot, 1 millivolt EEG. Unlike ECG, brain waves are irregular, there is no standard PQRST pattern, there is a irregular pattern and they vary continuously. So, to come up to a conclusion, you need longer recordings to detect patterns. You might not be able to see any patterns. If you look at these signals, are you able to see any patterns? This is just noise, it looks like just noise. EEG plots essentially show on the x axis you have time and on the y axis you have voltage, capturing near real time brain activity means the ensemble activity of it. So, this is quite often successfully used to detect epilepsy. This is a field in which EEG has been extraordinarily successful to diagnose epilepsy and other such related brain disorders. So, and epilepsy signal processing, EEG signal processing for epilepsy is an advanced field, relatively advanced field when compared with the rest of the EEG processing fields. There are other fields like sleep studies, alertness studies, cognitive studies, studying EEG to assess mental health, cognitive health, to assess depth of anesthesia, so many other ways in which you could study, and sleep health, sleep hygiene for example, all those things can be studied using EEG. Essentially these brain waves are electrical signals, rhythmic electrical signals that reflect different states of different brain states together. The fastest waves are above 22 hertz, 22 to 30 plus hertz sometimes can be seen when the person is focusing, like I am now giving a talk and you are listening, you are focusing a lot. If you are focusing, that is, the frequency might be very high, high level cognition and focus may be about 22 hertz and 30 hertz, or maybe even above 30 hertz in some cases. Beta waves, when the person is alert and actively thinking and attending to some external cues, attending to something external, or active person, that is between 13 and 22 hertz. Then alpha waves are between 8 and 12 hertz. So, this is gamma, very fast, this is beta, this is alpha, between 8 and 12 hertz. The person is alert but relaxed, right, linked to wakeful rest or anesthesia depth. So, the person is alert but relaxed, that is the state when you just wake up from sleep, right. That theta is deep relaxation, meditation, when you are meditating, when you are drowsy, very sleepy, those are the theta waves. And then you have the delta waves, which is the slowest waves when you are in deep sleep or when you are when you are unconscious, that is the delta. See, look at the frequencies, all these frequencies are there, and note that the frequency ranges are relatively small, and if I am measuring from these scalp electrodes, movement artifacts, even if the patient is not moving, there might be movement artifacts purely due to blood flow that could be reflected in these slow waves. The amplitudes and the frequencies might be comparable. How will you then filter this out? Those are practical challenges. We discussed some of this in the previous set of videos. We will continue our discussion. So, with this we come to the end of this video. In this video, we introduced EEG or electroencephalography, a method to study brain activity or brain electrical activity, and we discussed the types of waves in EEG. With this, we end this video. Thank you very much for your attention.